Hello everyone. Let me introduce you my best buddy Marty. Marty? Marty! So in this lecture what I'm going to do is to create a model that can differentiate whether a particular image has a cat or a dog in it. At the end of this lecture, let's feed in the image of Marty and see whether our model is able to classify it whether it's a dog or a cat. It's going to be a really interesting lecture. And let's get started. These are the three major steps involved in today's classification problem. The very first step is to pre-process our data, and the second step is to train our model, and finally test our model. So if we are not happy with our accuracy, we go back, change some parameters in the model, train it again and test it again. After downloading your data, you need to split your data into three different sets: training, testing and validation. Majority of the data would lie in training phase, about 70%, and testing data would be around 20%, and the rest 10% for the validation data set. This particular step is for unsupervised pre-training. Recent research have told unsupervised pre-training is not required for supervised deep learning applications. So I'm just mentioning it for your own information. And also one of the steps for in the pre-processing data step is to augment our data. Again, in our case, it's optional because we already have a lot of data and it's just two classes. So this step won't be necessary. Just in case you feel your accuracy is pretty low, you can use this particular step. So basically, in order to increase our data set, what we do is randomly flip some images, change the brightness, contrast, hue, etc. So by changing this, we create new data and make our data set larger. Now let's train our model. First step is to choose your own architecture. You can choose your architecture like AlexNet, GoogleNet, or whichever you want to try it out. Or you can also build your own custom architectures. And once you choose, you are finalizing your architectures, choose your hyperparameters. You need to change these hyperparameters to change the accuracy and minimize test error, and feed images on the fly, and main aim for during the first training iteration is to minimize the training error. During the test phase, the very first thing is to measure the test accuracy and see if the difference between the test error and training error is increasing. If it's increasing, it's likely the case of overfitting, and we need to use some regularizers like dropout, and tune your hyperparameters to increase your test accuracy. You can change your hyperparameters, and finally test your accuracy in the validation dataset. Import all the necessary packages first. These are the regular packages. I am importing TFlearn to define my layers, and I am also importing a helper function from Python imaging library called image, and these three for dealing with text files. And this particular helper function called image preloader from TFlearn helps us to load our images and feed it into our model on the fly without consuming much of RAM. Feeding our data into a model is pretty tricky. The reason is because our data set is huge, and if we are trying to load the image first and then feeding into a model, it will occupy a lot of our RAM, and it's really inefficient. The trick here is kind of to use a cafe style of way to load our images, on the we try to load the images on the file instead of loading it in our RAM. So whenever we call that particular image, we load it in those particular batch of images alone and then feed it into a model. So I'm using TensorFlow TFLearn's image loader function. So before we do that, we need to create a text file containing the directory of the images and that particular class. So the class would be on based of numbers. So here we just have two classes. So either give 0 for one particular class and give 1 for the other. So I've given 0 for cats, 1 for dogs. So let's go ahead and create the text files. First, create a string constant containing the directory of the images. So here I have stored all my images in this particular folder. So change yours accordingly, and create three different string constants containing the directory, and create a text file. So here I'm just declaring the name of the text file that I'm going to use later. So repeat it for testing and validation data sets, and split our data set into three different parts. So decide your proportion, how much you want to split. So I'm splitting 70% of my data for training, 20% for testing, and 10% for validation. This is my data folder. So here you can see it contains images of cats and dogs, but it has been saved in a format like cat dot some number in the extension of JPEG. Similarly for dogs, if you scroll down, actually I have to scroll down a lot because there's lots of numbers. Yeah, so dog dot some particular number and JPEG. As you might have noticed, the folder contains images of cats and followed by images of dogs, and the number of images, total number of images is 25,000. So the very first epochs of our training session will be only contain the images of cat, and it will be of a single class, and model won't learn anything. So it's very essential to shuffle the data so you have a nice merge of cats and dogs in all the data sets, and in all the patches went in the training phase. File's name image consists of all the names of images in our image folder. Once we have loaded this, I'm going to shuffle it. After shuffling, I have a nice merge of cats and dogs. So let's go ahead and write our text file containing the directory of the image followed by the class name. Firstly, I'm going to open my training data text file. So training data is nothing but the directory followed by the name of the text file. So once I have opened this, I'll open all the images after splitting. So train proportion is the percentage of that training data set which I'm going to use. So I'm going to use 70% of my total. So I'm going to load from the very first image till the 70% of the total images, and I'm going to find whether that particular image is a cat from the file name itself. So if it is a cat, I'm going to write a 0 followed by the file and the directory and the file name followed by 0, and if it is a dog, I'm going to write it as the directory name plus the file name. After a space, I'm going to give 1, and I'm going to close my file. And similarly, I'm going to do the same thing for testing and validation data sets. So I'll have three different text files. This is how my training data.txt file looks. You can see this is the directory of that particular image. This is the image name, and followed by the class name. For cats it's 0, and for a dog it's 1. Let's go and load our images and labels. I'm going to call my image preloader function. It does a very good job here. So train.data contains the location of the text file. Basically it's a directory and the text file, and mention your image shape, and image preloader function automatically reshapes into this particular shape, and of course this is in file mode, and this particular argument, what it does is it returns the labels in terms of one hot encoding vector. So instead of zeros and ones, which I described in the text file, it's gonna return an array containing 0 and 1. For cat, the array would be 1 0, and for the dog, it's gonna be 0 1. Similarly, repeat the same for X testing and validation sets. So let's see the shape of our data set. So we have around 17,500 training images, 5,000 testing images, and 2,500 validation data sets. And the shape of the image is 56 by 56 and 3 channels, RGB channels. And the shape of my label is 2. Basically it's an array of 2, and denoting the number of classes as 2. So this is a sample image, and this is the label of that particular image. As I mentioned, for dog the label would be 0 1, and for cat it will be 1 0. I have reduced the dimensions of my image to 56 by 56. The reason is because if the dimensions are more, it's going to use a lot of RAM, and the computation time is going to be a lot higher. So if you have a PC with a very good RAM, like 16 or like 32 to 64 GB RAM, feel free to increase the size, and don't go beyond 512 by 512 image size. Even if you have a bigger RAM, it's again the convolutional layers and the whole deep network, it's going to be a lot of computation, so don't waste your RAM in the file size. So I would advise you to go by 128 to 128, or if you have a very low RAM, like in my case I just have an 8 GB RAM, reduce the size of the image as much as possible. Let's go ahead and define our model. It's going to be pretty much the same as I described in the previous example in MNIST. If you have any doubt, please refer to that tutorial I've discussed in depth. So here I'm going to skim through. Very first thing is to define my placeholders. So my input image is of dimensions 56 56 into 3, and the label is just two values in one particular label value. So what I've done is, for the input image I have created a placeholder with none into 56 56 into 3, none because I don't know my batch dimensions, and it's always a good idea to give the batch dimensions as none so that you can change it later on. And for images, input class, so again the first dimension is going to be none, and I've given it as 2 because it's going to have two values, 0 1 or 1 0, and be sure to reshape it at the time of feeding into the model. So this is a modified version of AlexNet, so feel free to use your own model architecture, or you can follow standard architectures like AlexNet or GoogleNet. So basically it's again a series of convolutional layers and fully connected layers in a different fashion. So this is a general way to define such particular network architecture. So I have given 3 convolutional layers and two fully connected layers, and final softmax output layer. And I've used 128 filters, and the second and third layers, and 64 filters in the first convolutional layer. And for my loss, I've used maximum likelihood loss, and Adam optimizer. And since it's again classification problem, I'm just using the same thing as described in MNIST example. Since I'm in a IPython session, I have given it as an interactive session. I initialize all my variables, and since this is going to take some time, it's always a good idea to save your model. So give a save path where you want to save your checkpoints. This particular function displays all the operations in my graph. So you can see all the operations starting from and this is the layer name, and these are the operations. And you can change this accordingly to your hardware configuration and how many iterations you want to run. And if you have a very good hardware configuration, just change the batch size to 40 to 50. And if you are running in a GPU, give it in the terms of powers of 2. Like the batch size should be like 8, 16, 32, 64, 128. So since we are doing batch wise training, I've given a variable called a previous batch and equated it to 0. This is where my optimization starts. So the very first thing is to divide the input images and labels in terms of batches. So this particular few lines of the code takes care of that. And following a regular way of training and optimization, run optimization code here. And for every 500 iterations, I'm testing the value of my accuracy of my test set. So once again, because of lower hardware configuration, I'm just testing my accuracy in the test set with just 50 samples. If you have very good hardware, please go and change this number. As much we have around 5000 testing images, so any number between 0 and 5000 as per your hardware configuration, you just change the value of n, and you will be feeding those many images for testing your accuracy. More it is better, but since of hardware limitations, I am just keeping it as 50. And for every 100 iterations, I am going to print my loss. So let's see our output. I've already run it, so it's going to be, so every 500 iterations it's going to be printing out my accuracy. So as you see, for after a few iterations, the accuracy in the test set also increases. At the same time, loss also decreases. There might be some fluctuations, but don't worry about that. If you see some cases, the accuracy on the test set kinds of drops, and interestingly, the loss in the training set also decreases. This might be the case of overfitting. In order to avoid this, you need to use some regularizers, or go back and uh, increase the test set size and see if there's any difference, or you need to work on with the hyperparameters. Hyperparameters, for example, include the number of convolutional layer filters, and the dropout layer percentage. So I've just run for 5000 iterations here. So depending on your requirement for the accuracy, just increase the number of epochs, batch size, and the test size also. Following it, let's test the accuracy in the validation dataset. So now I'm going to feed my network with uh, images in the validation dataset. So I first reshape the input and the label input to two values. Alright, so this is my accuracy in the validation data set. It's around 80 percentage, which is a really good percentage for this particular data set. But I'm pretty sure if you are running for more epochs and add more layers, you will get a better result. It's now time to test our model with the image of Marty. Let's see whether my model is able to distinguish whether Marty is a dog or a cat. First, I'm going to import the image of Marty using the helper function I have imported from PIL. I'll display the image of Marty. Isn't he really cute? So I'll just rotate the image of Marty just for showing purpose. Even without rotation, my model will detect the whether it's a dog or cat, and I've tested it also. So let's process the image of Marty to fit into a network. The very first thing is to resize the image of Marty to 56 by 56, and then convert the resized image to an NP array. And once you convert into an NP array, normalize it, and after normalizing it, reshape it in a format friendly to our network. So this will be the batch dimension, or as we have given in the placeholder, it's none, 56 by 56 into 3. So this is the processed image of Marty. You can see there's so much of resizing here, but still it contains the essential features of Marty. So let's go ahead and predict it. So the first step is to feed in the image of Marty. So I've saved it as Marty test here, and I will feed into my network. And y predicted contains two values, and the value containing the argument maximum argument of that particular value will be the class. So as we have given before, 0 corresponds to a cat and 1 corresponds to a dog. So it's a dog, and my model predicted it correctly. I've also included a helper function to do the basic image processing task for testing out your own images. So it's called process underscore img. It takes in an image as an input, it resizes it, converts into an NP array, normalizes it, and reshapes in a format friendly to the input placeholders. So let's see how it works. So first open your own test image, and if you want to see, just click the variable name. So it's C1 here. So if you just press C1, it will display the image, and then just process the image, and then plot the image. So it's a very useful helper function. This brings an end to our lecture. I hope you all have enjoyed, and if you had any difficulty, please be sure to write in the comment section, or reach out to me in GitHub or email me. would be really happy to help you out. So I hope you have enjoyed this lecture, and thank you.